I want to talk about some more properties of random variables. So let's begin with just a little review here. Gain Communications sells aircraft communications units to both the military and civilian markets. Next year's sales depend on market conditions that cannot be predicted exactly. Gain follows the modern practice of using probability estimates of sales. The military division estimates its sales as follows. You can see the distribution here where units sold is our random variable and the probabilities. There are personal probabilities that express the informed opinion of Gain's executives. The corresponding sale estimates for the civilian division. All right, so take X to be the number of military, Y to be the number of civilian. Find the expected number of military units. So I'm going to just quickly talk, because we've done a lot of expected value. Just a reminder that the formula for expected value is the sum, let me write it up here, expected value is the sum of probabilities times random variable. So we would simply do 0.1 times 1,000 plus 0.3 times 3,000 and so on. If you actually calculated that, you come up with 5,000 as our expected military number of units sold. The expected number of civilian units sold. So again, same formula. In this case, of course, we'll do 0.4 times 300 plus 0.5 times 500 plus 0.1 times 750. And we end up with 445. Find the expected total amount of units sold. Well, I think you could probably guess. If we expected to sell 5,000 military units and 445 civilian units, we're planning on selling a total of 4,445 units. Find the expected difference. Well, again, if we expect to sell 5,000 military and 445 civilians, we subtract, we say, well, we expect that difference to be 4,555 more military units than civilian. And finally, if the company earns a profit of $2,000 on each military and $3,500 on each civilian, what's the expected? Well, we make $2,000, we expect 5,000 times, and we make $3,500, we expect 445 times. So that's equal to 11,557,500. Okay? Now, I put up here a little note about a mysterious important condition. And this condition, when we begin talking about combining random variables, one thing that's very important to know is, are those random variables independent of one another? Okay? Because once you start combining things, they shouldn't rely on one another. Knowing that the military division had a great year, if that tells us something about the civilian division, then the probabilities might change. So we should know that these things are independent. Otherwise, we shouldn't be combining them. Now, a lot of times the expected value, we can just combine. We don't have to worry about independence. But in just a moment, we're going to talk about combining standard deviations as well. And especially, I'm just going to make a note, especially for standard deviations, we need to know independence. Okay? I personally think it's nice to know overall, but really for our calculation of standard deviation, it's important. So let's begin talking about standard deviation for military units. So you remember the expected value for military was 5,000. Expected for civilian was 445. Please recall our formula for standard deviation is the square root of the sum of the probabilities times x minus x bar squared. Now, I'm going to pause and just calculate this very quickly. If you need a refresher on how this calculation works, go back and watch an earlier video of how it works. Okay, I've completed the calculation. I'm going to round to the nearest whole unit. The standard deviation here is 2,793. And the standard deviation here is 139 units. Now, find the standard deviation for the total amount of units sold. it's tempting to think you can just add them. However, when we are combining all of these things together, think about it like you were doing it as one long calculation. Okay, and you would say, well, I'm adding all of these variabilities together, 0.1, 1,000 minus 5,000 squared, 0.3, 3,000 minus 5,000 squared, and so on. Then you would drop to the next line and just keep adding. And why I bring that up is really goes back to some properties of square roots that you maybe learned way back when you were doing Pythagorean theorem. And that is taking the square root of 3, something like 3 squared plus 4 squared. That is not the same as taking the square root of 3 squared and adding the square root of 4 squared. Those are not the same. So we need to combine these things pre-square root, meaning we add the variances together. So we should never be combining standard deviations. We should be combining variances. So we should say, well, 2,793 squared plus 139 squared, and we take the square root. So if you wondered in the previous video why I talked about the fact that if you're tripling a random variable, you triple the deviation but you multiply the variance by 9, it really comes back to this. We should be working with a variance. That's the algebra we should be doing. It's just that there are times when the algebra dictates that it doesn't matter. It doesn't matter which one you adjust. But this is not one of those times because square roots aren't distributive. Okay? Find the standard deviation for the difference. Well, here's the crazy thing. It's the exact same calculation. Now, the statistical reason for why it's the same calculation is anytime we are combining things that have variability, we have a greater chance of variability. Okay, we've taken two random variables that in their own set have a lot of variability. When we combine them, we have a larger range of variabilities. I sometimes, with this example, like to think about, the range, and maybe that helps. And you say, well, the best possible or the worst possible year this company could have, according to this distribution, is selling 1,300 units. And the best possible year is selling 10,750 units. So if I find that range from best year to worst year, 10,750 minus 1,300, I come up with a range of 9,450. So this is the range of sums. Okay, I'm just going to make a little S for sums. That's the range of sums. Now the range of differences is like saying, well, what's the smallest possible difference? The smallest possible difference is if they both had great years, if this had a great year and this had a terrible year, they're only 250 apart. On the other hand, if this had a great year and this had a bad year, they're 9,700 apart. So I write that down. I say, well, 9,700, the biggest possible difference, minus 250, the smallest possible difference. Here's the range of differences. And notice they're the same. So there's another reason why these two will be the same. Okay? The big thing to notice is there are two things. You never combine standard deviations, you combine variances, and whenever you're combining, you add. Let's look at one final example. A relay team consists of members whose times are approximately normally distributed. So you can see these runners, their average mile time, their standard deviation. It says runner 3 by himself thinks he can run a mile in less than 4.2 minutes. Is that likely to occur? So looking at runner 3, he's normally distributed, so you say, well, normal, runner 3 is 4.5 and 0.14, so 4.2 would be here, and of course we just say, 4.2 or less. So using that normal CDF on our calculator, we can calculate his probability. It is 0.016, so I would say not very likely that happens. The distribution of possible team scores is approximately normal. Find the mean and standard deviation. Well, of course, the expected value, the expected total time, is simply saying, well, let me add up all of their individual times. I end up with 18.9 minutes. And the standard deviation, of course, we can combine all of these, but we need to combine their variances. Plus, excuse me, this is 0.3 if you calculate it. So finally, it says, suppose the team's best time to date is 18.4. What's the probability they will beat their own best time? Well, I haven't left myself a lot of room here, so let me put this problem right up here. We're under a normal distribution with a mean of 18.9 and a deviation of 0.3, and we want to know 18.4. And using our calculator, the normal CDF, we get a 0.048 probability. Now, I just wanted to talk really about combining random variables here, but I also want to just mention what's coming up, and that is the fact that we really don't have a way of saying, okay, is that likely or not? It seems like a low probability. Of course, the runner 3 by himself, that's a more unlikely race than the team combined. But we don't have a cutoff. It would be nice to have a cutoff and say this is what's likely and this is what's not, but we don't have that yet. But that is coming soon. All right?